Hello, I'm Park, a master's student in the Department of Artificial Intelligence at Korea University. I will now begin my midterm project presentation. Now I tell you about the topic I choose. I choose Korean food classification by Jin because first I become curious about understanding and classifying the unique visual elements of Korean food. Second, I use numerical data, but this time I want to experience using image data. Third, the process of understanding and classifying the complex characteristics of images is interesting. Fourth, I want to use image data to intuitively visualize the output of a model. For these reasons, I choose the project and proceed with it. Next, I'm explaining the modifications made to the previous project. Firstly, the model used for image classification has been changed from less than 18 to Vision Transformer. This change is made because VIT use a self-adaptation mechanism to consider the entire images, addressing the limitation of less than 18, which being relatively shallow, with only 18 layers, struggles to extract complex features. Additionally, VIT can model global relationships between image patches, improving upon the issues faced by less than 18 residual connections, which tend to underperform with complex and varied patterns in dataset. And VIT has the complexity to comprehensively understand the information across the entire image and discern correlations between distant parts, overcoming the limitation of less than 18, which primarily focus on processing localized information within the image. Secondly, I add to pre-processing task of masking images before model training. Masking allows the model to focus more on key features of the model image by removing or hiding irrelevant or disturbing parts of the image. Moreover, masking leads the model to learn features of real objects rather than their surroundings or unnecessary patterns, reducing overfitting. In addition, noise or unnecessary parts of the image can be removed during the masking process, which improves the performance of the model. On large and complex image data set, computational resources can be used more efficiently during training, especially with masking. Here I will the model I'm implementing, including only significant changes from the original code. I use the Fast AI library, which greatly facilitates deep learning development. Along with Fast AI, I store all necessary libraries required for the model implementations. Next, I define a masking function for background remover. First, I convert the given image into a numpy array and change it to RGB format if necessary. I then convert the image to grayscale and apply a threshold to binarize it. After that, I contours in the binarized image and use the largest contour to create a mask. This mask is applied to the original image to remove the background, and the result is returned as a PIL image object. This process removes background information such as the resulting image shown on the right, highlighting the main objects in the image and increasing the accuracy of image classification. I set up the Vision Transformer model for training. The images are split into training and validation set in an 8:2 ratio, and the images are resized beforehand. To enhance performance, various augmentation methods are used. Additionally, the model training improves the Vision underbar learners function to initialize the Vision Transformer model and evaluate performance using metrics such as accuracy and recall. This approach leverages the model's strengths in understanding the overall context of the images, making it well suited for complex classification problems. Before training, I use a method to find the optimal learning rate. This method starts with a very low learning rate and gradually increases it, training the model on a small scale and tracking the loss at each learning rate. Through this process, the learning rate that minimizes the loss is identified, suggesting an optimal learning rate for training the model. As a result, the loss graph displays the optimal learning rate marked by an orange dot, significantly enhancing the efficiency and effectiveness of the training. After finding the optimal learning rate, I proceed with transfer learning, conducting training over a total of 15 epochs. During the initial 3 epochs, parts of the model were frozen, maintaining previously learned features while only adjusting the remaining parameters. This approach is effective when applying a pre-trained model to a new dataset, allowing for rapid convergence and achieving higher performance. I visualize the result of the trained model. On the right, the images show the model predictions for 8 images. The actual labels are displayed at the top and the model's predict labels below, allowing for an intuitive understanding of the model performance. The results show that the model predicts all labels accurately. I analyze the result using a confusion matrix. The matrix reveals a reduction in the numbers of misclassified cases compared to existing results, indicating an improvement in the model accuracy. Finally, I generated various metrics to evaluate the model performance. The results showed improvements ranging from 1% to 5% compared to existing outcomes. This indicates that changes to the model and the enhancement in the image processing steps have successfully improved performance. This concludes my presentation. Thank you for listening. If you have any questions, please contact me via email. Thank you.